Okay,
So,
welcome everybody. I'm very happy to introduce Carlo Barenghi, who will give a talk on turbulence and knottedness. Carlo, to you.
hello. Hello to everybody. I'm Carlo Barenghi from Newcastle University. Thank you for inviting me here to give a talk at this online meeting. So today I want to talk about this question: is turbulence knotted? And to cut it short, the answer is that I do not know. But probably yes, that's my attempt of an answer. So I'm going to describe why one should ask this question, why is it interesting, and why my tentative answer is probably yes. So I'm going to talk about turbulence, ordinary turbulence, which you know very well from daily experience, and contrasted to another kind of turbulence which interests me greatly, which is called quantum turbulence. Turbulence in a quantum system, in a quantum fluid. And I'm going to try to convince you that problems of the kind which I'm going to describe, such as is turbulence knotted, are questions which are easier to answer in the quantum context because of the quantization, as you will see. But in this way, we sort of learn about the knottiness, the topology, the relation between topology and dynamics and geometry in other systems, perhaps sophisticated, abstract, not really related to ordinary life like a quantum fluid, but it has so many connections with ordinary turbulence that it is worth remarking. And perhaps we can actually, at the end of this exercise, we shall be able to use the tools which we have developed in a classical context. So let me say just why one should be interested in turbulence. Well, clearly the reason is simply that it is everywhere. Turbulence is inside us, for example, the blood moving in the aorta. It is around us in the air, which we breathe, in the water if we swim. So it's quite important for all sorts of natural, for the natural world. Applications range from the weather, the climate, to astrophysics. For example, the sun interior is turbulent. And of course, to technologies. For example, think of airplanes, airfoils, the mixture of air and fuel in jet engines, etc. So all these systems are turbulence. It is also a mathematical problem which is interesting. In fact, it is one of the 7 Millennium Prize problems set by the Clay Mathematics Institute at the beginning of the century. One of these problems has to do with the ruling equation of turbulence, the Navier-Stokes equation, and it has not been solved, unlike others. But turbulence is above all interesting to a physicist like me. So turbulence is a problem really of nonlinear statistical physics. We are dealing with a problem which is time-dependent and three-dimensional, which makes it complicated. But really the complication is that we have really a huge number of degrees of freedom which are excited together simultaneously and interact nonlinearly. And it is the nonlinearity which actually is the major difficulty. So we can think of turbulence, for example, by measuring something as a function of time at a fixed position. In this photograph, you see actually a NASA engineer in some landscape in a desert with little gadgets to measure the wind speed, and the measurement is represented at the right hand side. So you see some wind speed, the speed of wind at the height of about a meter versus time, and you see that it fluctuates in an apparently random fashion with violent fluctuations. So this is a way in which actually we see turbulence. We can also look at turbulence by fixing time, holding time, and looking at the space complexity. So this photograph shows a pyroclastic flow coming down from a volcano during an eruption. So this size of this picture is actually perhaps on the scale of a kilometer. So you see this big cloud and all this kind of broccoli shape of the shapes of the dust and all this very hot, pyroclastic flow. So this rounded broccoli shape is because there are vortices or eddies. And I invite you to think of the length scales which are present here. So you see things, kind of rolling things on the scale of many, many hundreds of meters, and then to the scale of the meter, and clearly it goes down to scales which you don't see in the photograph, like centimeters and millimeters. So if you think of all these length scales and multiply into 3 dimensions, you see that indeed the number of degrees of freedom which are moving together and interacting is really indeed huge. Now, I stress, what makes turbulence is really eddies or vortices. And it's interesting because, to me, because I'm Italian and I'm from Milan, and the kind of local painter 5 centuries ago was Leonardo da Vinci, who was quite interested in nature, as you know, and he kept notebooks where he wrote notes about almost everything. And he spent much time studying the motion of water, and there are some remarkable drawings which he made showing turbulent water. But the way Leonardo represented the water is actually striking, because he represented water being turbulent as a collection of 3-dimensional eddies. You see this sketch here, which is actually, I think, in a museum in England at the moment. And you see these round eddies, but you see the water coming from some hole on the right, a bit of a little fountain. Essentially, there is a waterfall into a small pond, creating turbulence, and the eddies are actually everywhere, at the surface, but also within the fluid. Now, if you think of other representation of turbulent water in the arts, in paintings, for example, you will never see anything like that. You see some kind of foamy mass, waves, etc., but you never see vortices. So Leonardo's insight was quite deep. If you look at this picture, I actually superimposed with my pen in blue the kind of direction of the flow of the eddies. You see some vortices being clockwise and some being anti-clockwise. And in red, I've represented what nowadays we call the vorticity. The vorticity, as you know, is the curl of the velocity field. So we have a field, a 3-dimensional field, the velocity at each position of time at any moment. There is like an arrow representing velocity, and the mathematical operation of the curl picks up essentially the property which I can describe as the local rotation. So that is indicated by the red line. So the red lines essentially are vortex lines. Let's call them like this. Now, it has many centuries passed before somebody else picked up on this drawing, which actually was not made public. I think it became known only in modern times. And I like to notice the gap between the times of Leonardo until Reynolds, who was the first physicist at Manchester University, who actually studied turbulence as a modern physicist, and also mention a German engineer called Hagen, who actually realized that turbulent flow actually contains eddies. He used sawdust to visualize these eddies, really in the same spirit as Reynolds, who used ink to visualize turbulent water. So, the best visualization, however, can be obtained nowadays with numerical methods, because we can actually go there in time or space and represent what we want. And of course, we find in this case very good agreement with experiments, so they're quite reliable. And what is the governing equation of this turbulent flow, which, for example, is represented in Leonardo's picture? Well, it is this equation, the famous Navier-Stokes equation for the velocity field, which you see here. P is the pressure. So some kind of evolution equation for the velocity, essentially representing Newton's second law for a fluid. And it's a fluid with a constraint. Constant density means the velocity field is solenoidal. So I want to stress that here we have a very messy, disordered solution for the velocity, which is disordered in space and time. But let's think of the vorticity. So we have a continuum velocity field, so the vorticity is also a continuum velocity field. So if we take like a box where we do our computation, or we measure the flow, we find that these vertical lines, these vortex lines, the curl of the velocity, are actually infinite, of course, and they fill the entire space. We can plot some for the sake of illustration, but we keep in mind that it is a continuum. But in reality, actually, turbulence is not a uniform random mass. It contains structures. It is actually more than chaos. And these structures are visible in this picture here, which I took from a paper by a Japanese scientist published in Journal of Fluid Mechanics. So what is plotted here is really somehow the square of the vorticity. So the magnitude of the vorticity in the regions where it is significantly larger than the average. So you see some kind of irregular blobs or kind of tubes. Some people call them worms, where there is more vorticity. So what is going on from the point of view of the lines of vorticity, the red lines, which are contrasted to the blue lines representing the velocity? So a region of intense vorticity can be described as a region, as you see in this diagram, which I made by sketching on top of Goto's original picture. Essentially, there is a concentration of vortex lines. Vortex lines get closer, although if we move away from this little kind of tubular region, then the vortex lines go everywhere, and they're all tangled up, and they look like random. So this is the essence of the turbulence problem from the point of view of describing it. It is a mess, but there is some organization, and these vortex lines are very much disordered. And a good question to ask is, what is the topology of these vortex lines, and what is the physical meaning of any kind of disorder? So the question whether these vortex lines are knotted actually starts at this point. And I would like to show you a little animation just to illustrate this feature better. So what I'm going to do now is, and I hope that you see it on the screen now. On the shared screen, you should see a computational box with an actual solution of the Navier-Stokes equation, a bit like the image which you have seen, which is now moving. So it's a movie. So you see that these irregular tubular regions of intense vorticity, essentially this self-organization of the vortex lines in some kind of tubes, is quite interesting because it's metastable. Is it moving? Yeah. Yeah, I hope you see that it is moving. So
it's okay.
Can you see?
Yeah.
So they are not stable structures. They get created, then they get destroyed, and they form and they get destroyed again. So this is, you see, you see some events which really recall like that's very similar to proper sausages or worms, some people call them. Okay, let me go back to this now.
What's the Reynolds number of the simulations you showed?
Oh, I don't remember that particular movie.
Okay.
Sorry, I don't remember. I have to go and
Taken
check.
from?
It's a paper by Goto in Journal of Fluid Mechanics.
Oh, okay. Is their work. Okay,
Yeah.
thanks.
And but there are many systems, fluid systems, which are disordered, which are like that. And here, for example, there is another another images of these strong turbulent vorticity regions, and essentially the same problem appears for the magnetic field when we are in a situation which, together with the fluid being turbulent, there is also a magnetic field which is turbulent. There are many analogies between magnetic field and vorticity, which I don't want to go to. And the picture which you see at the left is actually a snapshot of some time-dependent numerical solution of some kind of galactic dynamo, so magnetic field lines, So the plane, the red plane which you see, will be the plane of a galaxy, and all the blue lines are essentially magnetic field lines. So the situation of a disordered system of lines, infinite lines, is quite typical of many physical systems. Okay. And at this point, I want to change essentially the context. So there is a class of fluids which are remarkably interesting to me, and I hope that can convince you that they are indeed interesting, called quantum fluids. And in these fluids, actually, the problem of even describing this complexity of turbulence somehow gets simplified. So quantum fluids are fluids which are cold enough that they have undergone a process, a phase transition called Bose-Einstein condensation, something which was predicted by Bose and Einstein in the 1920s when they started applying quantum statistical mechanics to physical systems, to an ideal gas. And then it was discovered it has to do with superfluidity, essentially superfluid helium, and then in the late 1990s to other systems which are essentially small clouds of atomic gases. So the context is different, it's more of a context of atomic physics and people working with lasers. And then we have discovered many more quantum fluids. We just want to mention polaritons, which is essentially light coupled to two-dimensional excitations in a solid. There are also neutron stars, etc. But I want to tell you something mainly about superfluid helium, because in this context we have more information. And the picture which you see on the left is simply a little container in kind of bluish light containing superfluid helium. Why the bluish light? Because you have to be very careful with such a substance. It looks like water, it's transparent, it has a density which is about a sixth of the density of water, and a viscosity which is very little, something like 100 of the viscosity of water. But above all, it's very, very cold. Its temperature is only a couple of degrees above absolute zero, so you need special technologies to study it. And on the right-hand side, I stress that the atomic condensers are essentially studied using lasers, like you see here, by trapping a very small cloud of very rarefied gases. So this is our context. Very low temperature, ranging from the few kelvins for helium, millikelvins for the second isotope of helium, the second most common isotope called helium-3, and a microkelvin for atomic gases. So we are in a regime where thermal noise has been almost eliminated, and the fundamental properties of matter come about, as we're going to see. So these quantum fluids have some interesting properties. Essentially, they have a two-fluid nature. There is a component which is the actual ground state of the system, or associated to the ground state of the system, which is the important part. And then there is a residual of thermal excitations, which can be referred to as the normal fluid if these excitations have a very short mean-free path, like in superfluid helium, or they are called simply a thermal cloud, like in atomic gases, because the mean-free path is much longer. So this two-fluid nature must be kept in mind, but we can actually simplify the problem by reducing the temperature even further, and essentially we're left with only one fluid, which is the superfluid, or the Bose-Einstein condensate. So this Bose-Einstein condensate has zero viscosity. So it is a superfluid, like in the textbooks of elementary fluid mechanics. You study solutions of the simple solutions of the Euler equation. There is no viscosity. Well, this is a physical system which actually almost obeys the equations described in these elementary books. But so the really interesting property, the physically interesting property, striking property, is that the vorticity is not a continuum. And the reason is that these systems are quantum systems. So they are described by a wave function, and it is a macroscopic wave function. We're talking about macroscopic quantum effects. Perhaps you're familiar with quantum mechanics a bit. You heard that it describes small things like electrons or nuclei, etc. No, here actually we're talking about large systems. You can have liters of liquid helium, and perhaps tons of liquid helium if you have a large cooling system to keep cold the superconducting magnets which control the beam of particles in the Large Hadron Collider in Geneva. So macroscopic quantum effects. Now this macroscopic wave function is a complex field. It has therefore an amplitude and a phase. And let's write the amplitude in this fashion, like the square root of a density, and the phase is this angle phi, which you see at the exponent. So these two fields actually can be associated to a fluid. So this n will be a number density. If you multiply it times the mass, you get the mass density of usual fluid mechanics. And from the gradient of the phase, you can actually, using the prescription of quantum mechanics, so we're not doing anything arbitrary here, we can actually create a velocity field. And here, that is, I give you the result from the existence and the uniqueness of this wave function. We can actually prove that the only way in which we can have some circulation, not vorticity, which is always zero, but circulation, is when in space there is actually a vortex line, which is some kind of tubular region or linear region, which is the red line at the left, very thin line, which is essentially a whole of the density. So the number density drops to zero on the axis. The thickness of this line is very, very tiny. Typically for superfluid helium, it is about 1 angstrom. So it's the size of an atom. But of course, atoms don't exist really in a system like that, because we have a macroscopic wave function. Atoms are bosons, and they've lost, in a sense, their identity. There is a gigantic wave function which describes the entire system. So it's a very thin line, and you see that the velocity must have actually this field, which is strictly 1 over r around the axis. To be more precise, it is equal to a quantity kappa, which is called the quantum of circulation, which is Planck's constant divided by the mass of one atom divided by 2 pi r. So that is how the quantization kicks in. Vorticity is constrained to discrete lines which have fixed strength. Discrete vorticity, fixed strength. The thickness of this vortex line is also fixed. So let me show again. You see the vortex at the left. In red, the core of this straight vortex. Clearly, I just show a section of the vortex, because as any vortex can only terminate at the boundary or a free surface, or it must be closed upon itself. And in the middle figure at the bottom, you see actually essentially on the xy plane, where z is the axis of the vortex, you see the phase of the wave function. You see that it changes from minus pi to 2 pi, and that change of the phase corresponds to the velocity. So there are atoms actually going around and around, and the system has no viscosity, so the atoms go around and around forever. It's a vortex which does not stop. If you take a cup of coffee and you rotate it with a spoon, remove the spoon, the coffee will slow down. But if you start up in some way a vortex which is a superfluid vortex, it will go on forever. And at the right hand side, you see actually a sketch of the velocity and the density as a function of the radius. So you see that the velocity is strictly 1 over r, and that extends to the axis. But on the axis, there are no many, actually on the axis itself, the density goes to 0, so actually there are no atoms which move at infinite speed. Everything is well behaved. So this is a quantum vortex. And the most important thing is that it is discrete, and it has fixed properties. You can only change its length and its shape. Yeah. So turbulence in such a system, which is a fluid, as I said, liquid helium is a fluid, the atomic condensers are a thin gas. can be created very easily. In fact, it's difficult to avoid making turbulence. You can stir the fluid mechanically, and typically you can use propeller, bellows, you can use heaters, so excite the system thermally, acoustically. In condensates, atomic condensates, you can use lasers as spoons. So turbulence is easily created, and there are many, many techniques to detect these quantum vortices. Some are fancy, and there is no analogy in classical physics, for example, second sound, NMR. But other techniques are really the classical technique used by engineers to study turbulence in fluids, which recently have been extended to very low temperature systems. In fact, it was not an easy step, of course, to make something which works at room temperature to work near absolute zero. There is actually a gigantic step. But many things can be measured, so we can study this turbulence. And it is turbulence of vortex lines. And again, let me try to show a little animation. So I'll interrupt this and see if I can start another movie. Okay, right, so what you see here again is a periodic box, and there are some vortex rings which have been put into the box, and they are moving and interacting. So these lines can reconnect, and there are ways along these lines, and we're injecting rings. They also destroy each other. And, after a while, we can actually create a steady state. So this is a steady state of quantum turbulence. It's turbulence of vortex lines. Now, if you think a moment, let me pause it. And actually, if I pause it, you will see, for example, that, you see on the right, there is a very clear vortex ring. And all the other lines are really very disordered. I mean, they don't have a regular shape, but you recognize some kind of wavy kind of perturbations. They're called Kelvin waves. They were studied first by Lord Kelvin. His key paper was in 1980. But I want to stress that actually what you see here is simply the axis of these quantum vortex lines. You don't see the orientation. So you have no idea about the velocity field, which is actually produced by these lines. The velocity field actually is immensely complicated, because if you put together, when we represent only the vorticity, then the velocity which follows is already complicated. If you put together 2-3 vortices, if you have so many like this, it's very difficult to visualize. It looks like a random mess. But I stress that in the space in between the vortices, we have, one, a fluid which is in viscosity, which has no viscosity. Two, essentially we have a solution of the Laplace equation. There is no vorticity but the vortex lines themselves. And this kind of picture with these lines is not very dissimilar from the classical turbulence solution of the Navier-Stokes equation, which you've seen in the other movie. So there is immediately an analogy which we can draw. So we have tangled vortex lines, but here the tangled vortex lines which we see are only the lines which exist. They're not arbitrary. The tubular regions which I showed you before were arbitrary because essentially they depend, how many there are, how big there are, depend on the level of at which I decide to plot the square of the vorticity field, which is a continuous field. So it's very, very arbitrary. So here everything is very prescribed. This is actually the geometry of the solution of the wave function. Think of this as a wave function. Imagine the phase which actually goes around 2 pi around each vortex line consistently throughout the picture. So it's a very complicated kind of closed solution, if you want, phase, because it's the phase of the wave function, which is the key property here. And in between, there is nothing. Really, a trivial flow, the solution of the Laplace equation. So this is quantum turbulence, okay? So the question is this stuff knotted? Now here we have a periodic box, however. The calculation was done in a periodic box. So immediately there is a problem which appears. slightly technical problem which one should overcome, and there are ways to do it. And it is that, okay, it would be better, at least at the initial stage of investigation, not to have to do with a system which is periodic. It's better to have a system where the lines are actually closed loops, because then if say there are two vortex loops which appear to be linked, then they are linked, and there is no doubt about the nature of this linkage. You don't have to worry about what is the solution actually. Right, so I'm back. I hope I'm back to the PDF, and let me make it bigger again. Right, okay, I said something about condensers. So these are very dilute ultra cold gases. Here we just want to show how one can make it turbulence. Essentially it's by shaking. So using magnetic fields, essentially one can actually shake the region where these rarefied gases are confined, and this shaking produces turbulence. And actually here at Newcastle we're working with an experimental group, an important experimental group in Brazil led by Professor Vanderlei Bagnato. So we're actually simulating that experiment. You see some image of this turbulent Bose-Einstein condensate, atomic Bose-Einstein condensate. I just want you to look at the picture at the bottom. What you see is actually this cloud. You see that the background varies from light gray to dark gray. It's because this isosurface of the density is so fragmented that essentially the line of sight can cross the surface more than once. And in red and blue, you see vortex lines, these phase defects. On the vortex line can be thought as a phase defect because the phase of the wave function on the axis is not defined. So, because it would be like dividing the real part and the imaginary part of the wave function together, and both are zero. So in red you see actually vortex loops which terminated the boundaries of the condensate. In blue you see closed loops. So we have actually quite different geometry. It's mainly like a gas of random vortex rings. Okay, so for this reason perhaps the topology is simpler, so I'd rather concentrate on superfluid helium. We have more information, and that is what I'm going to concentrate in the rest of my talk. So here you see how we can model. So the two most popular models for quantum turbulence. One essentially is it's a nonlinear Schrödinger equation. It is called the Gross-Pitescu equation for a Bose-Einstein condensate. It's a nonlinear field equation. Notice the cubic nonlinearity. So it's the equation for the complex wave function psi. And then there is a second method in which we don't try to describe the core of the vortex, but we just look at the vortex as a filament in space, and we can actually model how it should move. So essentially it moves in the first approximation as a vortex line, a mathematical vortex line within an ideal Euler fluid, classical physics, essentially Helmholtz theorem, which is represented by this Biot-Savart law, which is a way of saying what is the velocity of an element of a vortex along a vortex filament as a function of its own geometry. So there is this integral. It's called Biot-Savart, and I think it was derived first in the context of electromagnetism because it gives the magnetic field created by distribution of currents. Here we get the velocity field created by the distribution of vorticity, which is the geometry of the system. Since the intensity of the vorticity, the strength, is that kappa which you see in front of the integral. And then there is a correction due to finite temperature effects. So this model is actually very much used because it has been tested, and so it's very, very reliable. And so is the Gross-Pitescu equation. Okay? So how do we actually, what do we know about the turbulence of this quantum fluid? Well, we try first of all to compare it to classical turbulence. So this is a one-slide lecture of classical turbulence. The person in the picture is Andrei Kolmogorov, famous mathematician who gave the name to the to essentially the very important process which takes place in a classical turbulent flow, which is the Kolmogorov energy cascade and the Kolmogorov energy spectrum. So, in brief, let's consider the simplest possible case of turbulence, when it is steady, when it is homogeneous, when it is isotropic. So being steady, essentially there is some kind of forcing of the turbulence, which otherwise would decay due to viscous dissipation. And the most elementary kind of property which we can describe, which is physically important, is the distribution of the energy over the length scales. But rather than length scales, it's convenient to talk of wave numbers. K is the wave number. So the total kinetic energy, which is the integral of the velocity squared divided by 2, integrated in volume, and multiplied times the mass, which we take as constant, can be represented as a distribution over wave numbers. The question is, and where is the energy? So which kind of length scales contain more energy? Or in another word, which kind of eddies contain most energy? Small eddies, which means small wave numbers, large wave numbers, or small eddies, which means small eddies means large wave numbers, and actually large eddies is small wave numbers. The wave number is the inverse of a length scale. And the answer is given when this energy spectrum, E hat, which is plotted here, written here in the middle of this slide. So the distribution follows this power law scaling, k to the minus 5 divided by 3. So this is often referred to as the Kolmogorov energy spectrum. So when we see that, we know that behind there is an energy cascade, there is a continuous process in which energy, which is actually fed into the system at large length scales, is transformed into energies at larger and larger wave numbers, which means smaller and smaller eddies, until when the eddies are small enough, the viscosity can actually destroy the kinetic energy and turn it into heat. So this is the route for the energy. It goes in at small wave numbers and goes out into heat at large wave numbers. And this, in brief, is the nature of the simplest classical turbulence which we can think of. And many years ago, actually, people did experiments with superfluid helium, and they measured this energy spectrum. I have two experimental pictures here, both taken in France, by the way. The first in Florence and the second in Grenoble. And they actually found, to their surprise, that although superfluid helium is a quantum fluid, if you look at this important property of the turbulence, it is the same as it has been observed in classical turbulence, okay? But it must be stressed, this is only true provided we don't ask what happens at very short length scales, which are shorter than the typical distance between the vortex lines. Remember that there is an extra length scale in our system. It is actually the distance between the vortex lines. In a classical system, you have only the size of the box, if you want, and the length scale at which the kinetic energy is destroyed by dissipation. This is often called the Kolmogorov length scale, so the large and the small length scale. In a quantum fluid, there is also another, the third length scale, which is the average distance between the vortices, because the vorticity is discrete. And essentially, here, these figures show that provided we have, we're looking at large enough length scales, larger than the distance between vortices, we see classical physics. And really, the reason behind that was explained in this paper in 2012. So at the left, you see like a computed vortex tangle of quantum turbulence with all these vortex lines, which have been color-coded, essentially, by their interaction. So when you see yellow, it means that the vortices tend to be parallel to each other and therefore rotate around each other. So there are regions which form some kind of bundles. It's like the green vorticity regions which you've seen in the first movie. The velocity field can adapt because the vorticity of these various discrete vortex lines is parallel to each other. So we actually create regions of large length scales. And when And when you see actually red vortex lines, it means they are random to each other. There is little interaction because the velocity fields cancel out. The lines are randomly oriented. And that gives two very different behaviors. And the total effect is dominated by this kind of bundling, the yellow bundles which you see here. So that is why there is a Kolmogorov spectrum, because of the spontaneous self-organization of the vortex line which create bundles. But actually there is another kind of turbulence which has been discovered in superfluid helium, which is quite different. It seems to be totally random. It does not actually like to create these coherent structures at all. And it has been called Wiener turbulence. And I don't want to describe too much of its property. It's quite different in terms of the energy spectrum, in the way it decays, on the correlation function is quite different, and so on. So this is actually what we know about these systems. And then the natural question is, okay, so is this quantum turbulence knotted? And briefly, I want to tell you what we know of this question in attempt to give an answer. And of course, there are lots of motivations here. Essentially, particularly after the experiment of William Irvine in Chicago, who managed to produce vortex knots in the laboratory for the first time, so in a controlled way. So we know for sure that it's possible to create vortex knots. There have been actually numerical papers, theoretical papers on knots, but this was the first evidence. And this kind of study also opened the way to questions of the kind, whether, for example, the turbulence, when it decays along routes, which are actually determined by the topology in a way which is simpler to understand than the dynamics. So what we have done here in Newcastle is a very simple numerical experiment. So we calculate these vortex tangles. We make sure that essentially the turbulence is localized in space. So we drive it, we find a way to excite the system and feed energy, compensating for any kind of dissipation, which even at zero temperature is there. It would be acoustic, or in other words, the vortex lines emit phonons. So we can maintain the turbulence in a steady state, and what you see in these diagrams at the bottom left, you see, for example, the total length of this tangle of vortices, which is represented at the top right, which fluctuates, and it is somewhat, look like random fluctuations in a very well-defined steady state. And at the right-hand side, I want to show an energy spectrum. So you see that actually most of the energy is at large length scales, at small wave numbers, and it's somewhat consistent with the Kolmogorov, dependence, which is k to the power minus 5 divided by 3, until you reach the wave number corresponding to the average distance between vortices. Then it becomes, as expected, a k minus 1 spectrum, which I don't want to explain. So everything seems to be very consistent. In terms of the properties of the turbulence, it agrees with the experiment, and we've done the tools which we have used have been tested in many other contexts. And also the ideas which we use to create the state of turbulence are also feasible in experiments. So the question is, okay, now we have vortex lines in a tangle, and here it is. So here I've tried to picture the lines with colors to describe the kind of the messiness of the vorticity. I stress the messiness of the velocity is even much more than what I can represent. And the question therefore is, are there knots in this kind of a messy region in which you see two snapshots here? And here I have a third snapshot. This picture was produced using knot plot, which is quite good for this kind of representation. So each color is a particular vortex line. You see, for example, some kind of spiral on the left, which is actually a Kelvin wave, which has been excited by the interaction with the other vortices. So you see some kind of long loops, like the kind of golden color loop, which seems to fill the entire system, and there are also some shorter loops. So how do we know whether there are knots here? That is not a trivial question, but it can be answered in a simple-minded way. So we want to distinguish knots from unknots, and possibly somehow to quantify how knotted the knots are. For example, keep in mind like the famous table of knots like this, produced by since the times of Tate, Kelvin's friend. And the way which we decided to use is quite simple. So we know that we can associate to a vortex, to each geometrical loop, it's simply a line which is closed upon itself. We can actually associate in an Alexander polynomial, which can be computed in this kind of standard way described in books. So now this is not a one-to-one way of representing knots, but it does capture the complexity, because if the degree of the polynomial typically tends to be very high for complicated knots. So for the unknot, which is simply the circle represented at the right as the figure A, then the degree mu would be 0. And then for the trefoil in this representation, it would be simply equal to 2. And then we go to the next knot of the knot table, and we have a 4, and so on, more complicated knots. But I stress, the knots which we have here have been produced by numerical simulation of a physical reality which exists in the laboratory. And they can be really awkward in the sense that they may have lots of complicated structures in a very small region, because that is what the dynamics, the equation, the Biot-Savart law essentially wanted to do. And we can only accept it. They are not nice like the knots which you see in the textbooks. But these are technical problems which must be solved, but this is the results. So this summarizes really everything. This is the probability that a given vortex loop is knotted. So lambda is the length, and P is the probability, and you see that provided one of these vortices, a vortex is long enough, you're almost certain that it is knotted. So it's, but that is not surprising, because it happens also it has been found in other systems. For DNA, for example, long molecules which can apparently become easily knotted, and also for some kind of toy systems like tumble strings put in a washing machine. So it looks as if that this system of vortices, which is actually obeys the Kolmogorov scaling of turbulence, although it is not classical turbulence, is a kind of simpler quantum turbulence, is without any doubt knotted. There are lots of lines which are individually knotted. It's also interesting to see which kind of knots we have. So here we have a time series where in red, at any moment, I'm plotting the largest degree of an Alexander polynomial. Essentially, I'm plotting how bad the knot is, how complicated the knot is. So you see, on this scale, actually, the degree can fluctuate wildly, because there are fluctuations, clearly, although there are well-defined means of everything which we can measure. So at any moment, there is always one knot which is immensely knotted, with the degree which, say 50, can go up to 100 or so. And if you look at the second most knotted knot, the second most complicated knot, it's not as bad, but still a very high order. I don't even know the name of knots of order around 10. So, in other words, the way I like to put this result, which surprised me because I expected actually naively a kind of smooth distribution, is that in any moment in this very simple kind of little patches of turbulence, which is actually similar under the most important respects to classical turbulence, there are monster knots. They're really very complicated, long, knotted knots. There are monsters lurking in the turbulence. And we can look, try to produce a spectrum of turbulence, essentially a distribution of these degrees of Alexander polynomial. And, well, there is some kind of scaling law, which we see in all the simulations which we have done. So perhaps I should not say that the power law is minus 3 divided by 2, because that suggests that I can actually prove it is like that. No, I should say it is about 1 minus 1.5, so it's just a numerical experiment. But there is a scaling law in the system. And I can do the same for links. So we ask the question, are these vortex lines, which are they are always closed loops in our system by construction, are they linked like a Hopf link, which you see? And of course, the linkage of the system fluctuates like everything strongly, but there is actually a very high kind of linkage, which is produced once you reach a statistical steady state, much higher than actually the initial random linkage, which is put by the initial condition. By the way, the results do not depend on the initial condition. That has been tested, and it's well known also. So we have knots and links. Now, I want to say something about the reconnections, because they are the kind of crucial mechanism which creates knots and destroy knots. So I heard of reconnection the first time I read this paper by Feynman, which was in 1955, on the applications of quantum mechanics to superfluid helium. And he had this little sketch. So he explained in the text near this diagram, which you see at the top, that according the quantum vortices should reconnect, but he had no actually motivation to say that, and now we know that they do, because all our models show reconnections, and also experiments like it's been done in various laboratories show reconnections. You see, for example, in the top figure, you see reconnections of vortex lines in superfluid helium. These experiments were done at the University of Maryland. So you see all these dots. They are essentially tracer trapped in the vortex lines, all aligned because they're trapped inside the vortex. And here they see vortex line coming together, colliding, and then they measure actually how they come in towards each other and move away. And at the bottom you see figures taken from, again, in the laboratory in atomic condensers at the University of Trento in Italy. So we've been part of this project. And you see, vortices which they approach and reconnect. So this is, Feynman was correct. There are reconnections. There are also in classical physics. People can solve the Navier-Stokes equation and study the reconnections of vortex lines in the context of the Navier-Stokes equation, although what they have is simply reconnections of very thin vortex tubes. So there is a natural question whether there are universal properties of these phenomena which are actually the building events of any kind of complicated flow. You cannot make anything non-trivial in a fluid if you don't include some reconnections which makes you to depart from something which is basically a solution again of the Laplace equation again. And there have been many speculations on this. Many quantities have been proposed and investigated, such as the cusp angle, or there has been an idea of like a cascade of vortex ring scenario. And it looks as if there is actually a universal quantity, which is the minimum distance between vortices, this delta, which changes with time. And we found that actually there are two possible scanning laws, which have been actually verified in all the experiments and the numerical experiments using all models which we can put together. So we never actually from that. This scenario, there are these two scalings, and also one scaling was known in classical physics. There was a paper by Hussain in Texas and collaborator who solved the Navier-Stokes equation for the connections, and then after our paper he discovered also the second scaling. So there is some kind of universality in these reconnection events. Which, as I said, what produces the topology and destroys that and reproduces it again. So I think I'm at the end of what I wanted to tell, so it's not much. So if there is something which I would like you to remember is this, that quantum turbulence is very much constrained. Quantum mechanics and the fact that we do not have viscosity means that the turbulence in a quantum fluid is simpler, there is no viscosity, vorticity is constrained to lines, discrete lines, essentially moving in a vacuum. The strength of the line is fixed, unlike what happens in a classical fluid, and still we see some kind of crucial properties of classical turbulence, such as the Kolmogorov cascade. So it's quite exciting in a sense to see that a quantum fluid can reproduce, in a sense, the skeleton of classical turbulence. But it's not actually so simple, because we also found that there are also systems, regimes, in which the turbulence does not behave as a classical fluid, and it is what we called Wiener turbulence compared to Kolmogorov turbulence. And in any case, because of the discrete nature of the vorticity, we can actually easily quantify the knottiness. And we find, therefore, that indeed the turbulent flow, which obeys the Kolmogorov spectrum, like classical turbulent flow, is knotted. And it's not in a funny way, in the sense there are strong knots, and then there is a moderate number of smaller, much smaller kind of knots, but there are always strong knots present in the flow. So at this point, I can only give you some references if you're interested more in looking at this kind of problem. These are recent papers, and I can only thank you for listening. And if you have any questions, do not hesitate to ask.
Thank you very much, Carlo. Very interesting. Of course, I welcome questions from the audience. If anybody has a question, I'll have one just to start off. I wonder how so I imagine you ran many simulations in order to get this knot spectrum and to be confident on that. How many simulations did you run?
Yeah, quite a number. We changed the initial condition, but like previous experience, not motivated by the topology, motivated by other physics problem, sort of also told us that things don't depend on the initial condition. And actually, you can create a data set which is as large as you want, because once you reach, essentially past the initial transient, then in all the systems, whatever you test is actually achieves a statistical steady state. Helicity, linking number, crossing number, everything achieves a statistical steady state, and we made sure to have very long time series, so we can average tens or hundreds of data points along this time series, and it's always the same. We simply change the arrow. Although it must be said that these are not very big systems. The Kolmogorov spectrum which I showed for this particular simulation is not very good in a sense. If you do actually a calculation in which you want to show whether there is indeed a k to the power minus 5 divided by 3 scaling, okay, you can use a periodic box, use a big cluster, and you can get a very smooth spectrum which has been done by others. Everything fluctuates, but you can reduce the fluctuations. There are, however, properties which are more sensitive to fluctuations. For example, the linking number. As you can imagine, there are lots of reconnections taking place any second. So reconnections destroy knots, but they also create knots. So if the system is smaller, you get large fluctuations. Perhaps that's the most sensitive quantity, which depends, if you want, on the size of the system. So I think we're pretty confident in this. But we do not know, as tests, whether the Violent turbulence actually is similar. And we've never done it because the distinction between turbulence, Kolmogorov kind of Violent kind is recent, and also because we had this motivation. The initial motivation, as I described, is turbulence of water or air knotted. So there is something which I want to add. There is an energy loss every time you make a reconnection, okay? So all these systems are the open systems. We need to feed energy to compensate for the losses. So reconnections are the kind of building event which creates the topology, but one also should think that energy is packed into reconnections, because it costs money to actually make two vortices to come together and cut and paste, and you make a knot, and you release energy if you want when you undo the knots. So it looks at any moment part of the budget is in the topology. That is the message.
Well, I just like to know something else. This is really, suppose you group your Alexander degrees in 2-3 sets, say, the very low degree, intermediate, and high. How robust would be this kind of classification against the numerical simulations?
I don't know. I've never tried that. as I said, since we started wondering whether there is a distribution and what it is like, my initial guess was some kind of Gaussian. Then we noticed there is always one, at any moment, a large knot. And the second is quite a kind of much less, much less Alexander, but we never tried to separate out, the effects better. We need bigger simulations for that.
So, Carlo, how randomized are these knots that you get at steady state? You got the long red one and the shorter or the smaller or less complex blue one. For example, do you know that these are highly composite knots? Do you ever see composite knots in there?
I do not know.
At least according to the Alexander polynomial, it would be possible to check the small ones anyway. Well, I mean the low complexity ones, the blue ones.
Yes, it can be done. It could be done in principle, yes. Indeed, most loops are not knotted. There is a large amount of tiny, small vortex rings. That depends on the dissipation level, because when for a high dissipation level, essentially depends on temperature in the physical system, smaller loops can get, eliminated. Can be done. We need to restart simulations of this kind to do it.
Also, in the linking number, you had them where the linking number actually goes to 0.
Yeah, occasionally the linking number is not very large in this in these particular simulations. As I said, the system is not very large. The linking number may go to 0, but it is an accident, and then there is a reconnection and it jumps. So it's if you look.
This brings up another.
Yep.
I'm sorry. Yeah, sorry, Carlo. What you were saying?
No, that one would need to apply this to kind of simpler situations. It can be done on a big cluster using periodic boundary conditions of the kind used recently, for example, by Giorgio Kustulovic, using actually the Gross-Pitaevsky equation. And if you look at his recent paper on the scaling of the circulation, because there is a scaling of the circulation, it's quite, you see a formidable kind of so dense kind of tangle of vortices, you can't even plot it, because it's like, the entire page is filled with ink. So one should move to large-scale simulations of this kind. But at the moment, I'm actually working on actually the condensate size of turbulence, where actually I think there is little topology, because the system has, the turbulence tends to have small rings and lots of immensely strong waves. So it's a different beast, very different from other quantum turbulence systems. It's not Wiener, it's not Kolmogorov. In some sense, it's a mixture of Wiener turbulence and what people call weak turbulence for waves. Because the spectrum of density fluctuations, the Zakharov, Nazarenko kind of side of things. It's a very interesting kind of problem when you mix turbulence of waves and turbulence of vortices.
May I come in?
I had the curiosity. Oh, sorry, Gunnar. Go ahead. Gunnar, go ahead.
I was wondering whether you have in your simulations vortices of higher quantum number.
No.
Or whether they are all so unstable that you never see them.
No. So in the model used, the quantum of circulation is strictly 1. But in the reality, it is also so. And you can try to sustain vortices which are multi-charged, but with great difficulty, and you need to be in a special environment. Essentially, the reason is that for a given angular momentum, there is more energy if you try to pack, to have winding number of two quanta. It breaks immediately. That can be tested easily. For example, the Gross-Pitesky model, we actually describe this beautifully. You can actually start with the vortex with, I don't know, 4 quanta. I've done it, and you see how it splits. It's a very...
How does it do it? It's just one ring into a pair?
Yeah, it's a kind of subtle thing, because the way it happens is that it must conserve the angular momentum, yeah? It splits, and then in doing that, also some energy goes away as sound waves. But there is a possibility that we have a paper on archive, I think it's still on archive, where we describe essentially how these waves, which are generated by these kind of protovortices, because they are so close in that limit, they are within each other's core, kind of tube. The interaction between, if you want, the acoustic side, the waves, and the vorticity is such that actually it cannot fall apart really easily and kind of open up, like it would happen if you allow, if you allow the sound to escape. So there are interesting problems, but for practical purpose in the experiments of this kind, no, there are only quanta of one. In atomic condensers, it's possible actually to create, as initial condition experimentally, multi-charge quanta, and I've seen beautiful photographs of, essentially vortex splitting immediately. Mm-hmm. So these vortices are very elementary. So the strength is fixed, is 1 quantum. The core size is fixed. The only thing which can change is the length and the geometry. The line can be curved, not curved. So it's very geometrical in a sense. Everything is in the geometry. That's why, that's my claim. The topology then can be seen better, because there is nothing else besides this geometry of a line which you can plot.
Thanks.
My curiosity, Carlo, was that you brought up the question of linking numbers, and as far as I remember, there is a difference between condensates and superfluids, among other things, and one is helicity. It seems that helicity in superfluid helium can take values different from 0. I remember our work as well. And in GPE is always 0. Do you have any comment on that?
No, okay. So there have been various papers about what should be the superfluid helicity. The problem is very simple initially, because naively one would say, okay, so we have a quantum system, there is a wave function which is complex, and we know, and there is no escape from the fact that the velocity field is the gradient of the phase. I mean, this is basic quantum mechanics of the 1920s, and that we cannot change. It is really so. So that means vorticity is equal to 0, and then the velocity field is scales like 1 over the distance. So when you try then to put that into the formula for the helicity, you have a puzzle, because you see a kind of contrasting effects. The vorticity is 0, velocity diverging. So there are possible escape routes. So there is a line of thought for which actually the helicity can be defined, and it is strictly equal to 0. And it's a consistent, I appreciate, it's a consistent mathematical line of thought. So it's conserved and it is 0. There is another line of thought, however, which attempts, in the context of a dilute gas, so it's the context of the Gross-Pitesky equation, to define a helicity, essentially taking more carefully into account how the velocity and behave, and the density behave near the axis. From that point of view, one can compute from Gross-Pitesky some kind of helicity, and then the good question is it conserved? And there is not a clear answer. It seems to be moderately conserved in some cases, but in others it doesn't. So it's an open question. There is not a theorem which says it is conserved. However, there is another line of thought, which is my own, which essentially goes along these lines. Okay, So the Gross-Pitarski equation applies very well, that we know, to dilute gases, although there are lots of effects which are outside, and we know actually about those effects. The thermal effects actually are not described by Gross-Pitarski. You need actually to modify it, and it gets complicated. There are also quantum fluctuations which are not taken into account by Gross-Pitarski. So it's a model, but at the moment most experiments are very well described. However, superfluid helium actually is not a dilute gas. It's a liquid. Essentially, the atoms interact much more strongly. In fact, that has been known for a long time. So, for example, in the spectrum of the elementary excitations of superfluid helium is not what is predicted by Gross-Pitarski, which is essentially phonons plus free particles. There are excitations called rotons, which were taught by Landau, and he really guessed very well what, the existence of these excitations. And so it's much more difficult to handle. Gross-Pitarski is only qualitative model in this context of helium, and there are attempts of making better models. Essentially, they involve Monte Carlo techniques to solve n-body quantum mechanics. They are really difficult in the sense that you can take only a limited number of atoms, and you in 2D, in 2 dimensions, you cannot do any dynamics. The best which people have succeeded in doing is actually to find a solution for the vortex core. And if the energy is less, it's a better solution, because that is how nature tends to be. And actually, the lowest energy solutions are found when one lets typically the initial guess for the wave function, for the wave functions of the atoms to evolve, because in the past, when that was first attempted, people used like an initial wave function in which the phase, the total phase was simply the sum of the phases of the atoms. So if you do that, you end up creating a singularity on the axis of the vortex by construction. It's not actually something which you discover. It's something which you put in, perhaps without knowing from the very beginning. So now actually the calculations are better, the energy of the vortex is less, and the vortex which is produced by these calculations has less energy, and actually, surprisingly, it looks more like a Rankine vortex. So the core actually has a density which is not zero in the center, and the velocity field increases with the distance up to the distance of 1 angstrom. I stress, 1 angstrom is the size of atoms, but here we're talking about a system which is not granular because it is atomic. It is actually continuum because it is quantum. There is the atoms are described by wave function. So it's kind of paradoxical, because you would think that if you look at smaller and smaller scales, then you end up with atoms, so you lose the continuity of matter. Well, not at all, actually. You go past that, and then you recover continuity, but of the wave function. So the vortex has a structure which is Rankine. So if it is Rankine, then, strictly speaking, there is no problem with the helicity, because velocity actually can happily, it has no problem, because it is actually solid body rotation near the axis, where the density is not zero, and then a classical formula like Kitt-Moffat formula is perfectly correct. Of course, we are not at the stage of doing dynamics with these models, not at all, a long way far, and probably. However, if you try to make a model of these superfluid helium vortices, which are on much, much bigger length scales, well, you should know actually what you are aiming at. And for helium vortices, it's something like it's a Rankine vortex, like a tornado, like a hurricane, or it's this kind of classical vortex. So the formula for the helicity actually would make sense. Although you cannot apply it to the very small scale. You can only apply it at the scales which are immensely larger, which you compute. However, what I discovered in doing that is that the formula of Kitt-Moffat for the helicity also has a physical meaning. It describes essentially some kind of interaction between the vortex lines. It tells me whether the lines feel the presence of the neighbors more or less. So it has a physical meaning to me. But I cannot prove anything in terms of conservation laws, etc. It's just a remark. So it's a long story. Sorry for the long answer. I think it is an interesting question, but perhaps to make progress, we need to, we can ask a precise questions. Like the question about Gross-Petersky is a well-posed question. I think there is perhaps there is a well-posed answer. The physics in general, I don't know, as often you make a step and you actually keep opening more doors than you can actually think you solve.
Thank you. Other questions?
I don't know if this is what the web was getting at, but whether you get large prime factors to depend on the density of the vertex lines in the volume.
Not understand.
Which question was, when you see the knots, do you get composite? In other words, many trefoils maybe, or do you get a big prime knot that can't be decomposed? What I'm saying is, that might depend on the density of the vertex lines in the bars.
Yeah,
That
I've
makes
not.
sense.
Sorry, the sound is bad. I can't understand.
I think one aspect of Greg's question was about your type of knots. If you have prime knots, how likely you get prime knots, and then the question was maybe Greg, you can help me if it was related to density.
Yeah, density of the vortex line itself. Does the density of the vortex line influence the primeness of the knot that you get?
Exactly. Yeah.
Okay. In the experiments in helium, people indeed measure the density of vortex lines because the experiment is the typical size of the experiments is much larger than the distance between vortices on the average. So that is a well-defined quantity. But the numerical simulations which you've seen is actually quite small. You've seen actually the entire thing. So you see a few vortex lines. The flow is complex enough that already starts showing the Kolmogorov scaling, although it is very poor. But I've not even attempted to measure, whether the density of vortices is uniform in this kind of spherical region. Probably it is not. Like in an atomic condenser, where the actual density and also the density of vortices is not constant. The system is too small. We need a much bigger system to answer these questions.
I have one more question. The rate at which the vertices separate. You had two regimes, square root of t and t. Square root of t sounds like random motion. T sounds like you need a reason.
You're asking about the two regimes. Let me put the question, the picture. I think it was this. See if I can actually. Sorry, I need to find the bottom. There is a motion sensor in my room, in my office, which stopped working. So if I sit too long at my desk, the light switches off. So, so here it is.
That's it.
Yeah. So the question I understand is the meaning of these two regimes. Okay. This linear regime is seen, for example, when there is like a relatively straight vortex line which is hit by a rapidly moving vortex ring. So this scaling comes about essentially in line rings collisions or when the motion of the vortices is induced by density gradients like delta rho divided by rho. So that happens in Bose-Einstein condensates because that is a context which we consider. So, for example, in the bottom pictures, these are vortex line in atomic Bose-Einstein condensate. The density actually is not uniform. It changes very strongly with space around in the system. So this is a possible parameter of the problem. Delta rho over rho would give essentially a scale, a velocity scale, kappa times that. So in that case, you end up with this scaling. The square root scaling is more typical of the interaction between vortices. Okay, that is the most seen kind of scaling. And also, when actually the lines get very, very close to each other's, so this is the time after the reconnection, the time to the reconnection or from the reconnection. So in this regime, essentially, just before or just after the reconnection, it's always t to the square root of time, and that is actually, the reason it is so was discovered by Nazarenko and his student West. Because it makes sense because, indeed, in that regime, essentially the axis of the vortices fall inside the vortex tube of the other vortex. So the density has been depleted. The density is the psi squared. So the cubic nonlinearity of the equation becomes very small, and you end up with essentially a behavior which has this regime, which is typical of the linear Schrödinger equation. So very, very near the reconnection, you are always on this branch, the bottom branch, but you may come out, and we can also predict actually, when, at which time and which length scale you come out of this. You go from red to blue.
Thank you.
It's quite an
Other
interesting
questions?
thing. Yep.
Yes,
Shin,
Renzo?
go ahead.
Renzo,
Yeah?
yes, thank you so much. Carlo, may I raise a question about the definition of energy in quantum fluid? According to my memory, in the area of MHD, when we are talking about the magnetic nodes, they are magnetic tubes. So the energy is defined about the story happened within the tubes. That means all the energy, we can just say this, all the energy is confined within the tubes. But for quantum fluids, the definition of energy is based on integral all over the whole space, right? Psi square or something, right?
But that
Can
is
we
true,
just can we just develop a new definition?
The energy of a vortex is not actually in the tube of the vortex or the axis, etc. It's in the space around it, because it's the kinetic energy of the flow around the axis, and the magnitude
Yes.
per r.
Yes, but that is just my question. Can we just find a way to develop a new definition for the vortex energy in quantum fluids? For example, can we just use heating length or something as the radius of the tube or something like that? Yeah, because I'm always unhappy about the
I think the situation is slightly confusing for this reason. In the Gross-Pitaevsky model, the total energy, of course, the Hamiltonian of the Gross-Pitaevsky Hamiltonian is conserved, but there are various contributions. You can recognize a contribution which is the interaction energy, the interaction of the atoms. There is a kinetic energy, there is also potential energy. And the kinetic energy, which comes about from, I don't have on the slides the Hamiltonian, unfortunately. That's too bad. Do I have the Gross-Pitaevsky equation somewhere? I think here. Yeah, here it is. So here you see that the first term at the right-hand side of the equation essentially is the term corresponding to the kinetic energy. So we think that the gradient h bar, and the gradient make the momentum operator, and then p squared, which is the kinetic energy, will be divided by 2m. It's this term. So this is the kinetic energy term. So there is a corresponding term in the Hamiltonian, and the Hamiltonian is conserved, but it's conserved in this fashion. The total Hamiltonian is conserved, but there can be an exchange of energy between, say, potential energy, which would be described by the term which creates this in the equation, the interaction energy, which is actually psi fourth divided by 2 times g in the Hamiltonian, and the kinetic energy, which is essentially this term. So there can be an exchange, and you see that all the times. So there is an exchange of interaction energy, potential energy, kinetic energy. On top of that, the kinetic energy can also be decomposed into compressible and incompressible, essentially one associated to sound motion, the other associated to vortices. So you can have these exchanges while the total energy is conserved. And that is because we have Grosspitaevsky, and the vortex axis is a region of zero density, so we allow the density to change. If we have the Biot-Savart model, essentially we're describing a system at much bigger length scales, and therefore it makes sense there to think that the density is constant. So the only energy is the kinetic, if you want, and there is no sound energy. So when we want to define the energy, we need actually to first of all, to specify whether we're talking about an incompressible model like this, Biot-Savart, or a compressible model like that, where we can have these energy exchanges, which are very visible in respective contexts. In the experiments, the effects are visible. In the calculations, you see them. So, but in general,
yes, very well. I think I should come to a stop probably to free everybody from the meeting. If you have any other question, please speak up. And if not, I'll bring this meeting to a halt. Thank you very much, Carlo, for a wonderful talk. Thank you.
Thank you for inviting me.
Thank you so much. Thank you.